Okay, exercise 7. Triglycerides are a type of fat in the bloodstream. The mean triglyceride level in the United States is 134 milligrams per deciliter. So the mean is 134. Assuming triglyceride levels of the population of the United States are bell-shaped, normally distributed means bell-shaped. All distribution, guys, are assumed to be bell-shaped with a standard deviation of 35. So sigma is 35. You randomly select one person from the United States. What's the probability that this person triglyceride level is less than 80? So you guys need to find probability of X less than 80, which we use the formula Normalcdf. Okay, we need lower bound, just to remind you. We need upper bound, we need mean, and we need standard deviation. If you want to see a sketch of the area that we need or the probability that we need, it's this. This is the mean right here in the center, which is 134. And 80 guys will be below, so will be somewhere here. And he wants what percent of people in the United States have a triglyceride level less than 80. So what would be the lower bound in here, guys? If I highlight this one right here. Lower bound would be what? It's a negative number toward the left. You can make it as negative as you want. So just use -1,000,000, I said yesterday. Upper bound is the end of the shaded area, which is ends at 80. Mean is 134, and standard deviation is 35. And let me do this. I'll use the calculator, the older one. Okay, so you go turn it on, second, distribute. Normalcdf, we don't use number 1, guys, it's just number 2. And we'll be using number 3 today, and that's it. Normalcdf, -1,000,000, comma, don't forget the comma, it won't work without a comma. 80, comma, 134, comma, 35. Close parentheses. It's 0.0614. If you want to change it to a percent, it will be 6.14%. Now, while doing the homework, you might be asked the question, is it usual or unusual to find a person in the United States with triglyceride level less than 80? Well, you say it's usual because it's more than 5%. If it was less than 5%, then that would have been unusual. And here's the screenshot of the calculator, guys, as well, but we did it right here. Any questions about the use of the calculator? If you didn't have the calculator and you had to do this one, guys, this is what you had to do. You need to change 80 to a z-score, which is going to be 80 minus 34 divided by 35, and then go to table 4 and look up the area. But with the Normalcdf, you don't need to change to z-score. You just put the lower bound, the upper bound, the mean, and the standard deviation, and then you get the answer. Any questions? All right. I'm not sure about the TI Inspire. It has to be 4 arguments. You just go to YouTube and try to Google how to use Normalcdf on the TI Inspire and get the information. I will only support the TI-84 in this class. Any form of TI-84. It could be this calculator, or it could be that one as well. But you should be able to do it, you know, just on the TI Inspire. Okay, section 3. We're in section 5.3 now. This is beginning of section 5.3. Okay. Let's tell you what 5.3 is about. Finding values given a probability. In the previous section, we were given a value and then you were asked to find the probability. In this section, guys, we're going to work backwards. We're going to give you the probability and ask you to figure out what the original X value was. So in this section, we'll be given a probability and you will be asked to find the value of the random variable. Okay. Let me show you a question here. He gives you this area here, watch. He said this area is 0.3632. He wants the z-score. He wants this value. Any ideas, guys? How would you figure this out without using technology? So what would you do without using technology? Can you guys tell me what would you do to find this z-score? He gives you the area to the z-score, the area to the left of the z-score, but he doesn't tell us what the z-score is. He wants us to find it. Any ideas? Yes? Okay, look what you can do, guys. You go to table 4. Since the area is less than 50%, you go to the negative z-score table right here. And you look up inside the table for the area that he gave you. He gave us 3632. That's the area he gave us. And we want the z-score. Look at the z-score, guys. You can find it. Watch. The z-score can be found in the first column in the first row. Right here. And right there. What is it? 3632. Okay. Right here. So it's negative 0.3 and then 5. So it's negative 0.35. This is how you can find it using the table. I demonstrated this here, guys. I put a screenshot. Look, this is the 0.3632 right here. And look, this is the value that corresponds to it, negative 0.35. Now, let's say he gives you an area that's not in the table. Let's say he gives you an area that is, for example, 0.40. The area is 0.40. How would you find the z-score? Well, you have to find, you know, the value that is closest to the 0.40. If you go here, guys, for example, 0.40, this is a close, it's 0.4013, and then you'll find the z-score, which is, if you read it, negative 0.2 and then 5. So you can do an approximation. But once you learn how to use the calculator, you don't need to use the table. Now, I could have found, you know, this z-score using the calculator by using a formula called inverse norm. So I'm gonna explain how to use the formula, and then we use the formula. You need 3 arguments here. You need area to the left of your value. Then you need mean, and then you need standard deviation. Since we're working with z-scores, we already know what the mean is. Mean is 0 and standard deviation is 1. Okay, what is the area to the left of your value, guys? He gave it to us. This is our target, and this is in blue. It's on the left, so it's 0.3632. And watch, let's go and use a calculator and show you how to find this one. So this is the second program that you will be introduced to today. You go to second, distribute, Normalcdf. Sorry, not Normalcdf, number 3. Inverse norm. Okay, you need to enter the area on the left, which is 0.3632, comma, 0, comma, 1, close, Done. Negative 0.35, guys, if you round to 2 decimal places. Actually, the calculator is more accurate. Any questions here about how to find the z-score given the area to the left? Now I'm gonna ask you a question, guys, and please, I need some participation, guys. You can text, you can talk. I don't wanna run the show by myself, just me. Let's say he gives you the area to the right instead of the area to the left. You have this, watch. And let's say this is 0.289 and he wants z. Any ideas how can I use inverse norm to find it? What would you do? Remember, inverse norm is programmed to accept areas to the left of the target.
Wouldn't you have to find the area to the left and then subtract by 1?
100%. So you'll do 1 minus, which is 0.711. Okay, and then you go to your calculator, you put 0.711, and then you put 0, and then you put 1. Let's do it. So always provide the calculator with the area to the left. I'll tell you something, guys. Even if you put 0.289, you can tell that your answer was wrong in a second. I'm going to show you why. How can you tell? So let's do it the correct way. Second, inverse norm. So what did we say? 0.711, comma 0, comma 1. Done. So the z-score is 0.56. Okay, let's say by mistake a student did 0.289, which is wrong, guys, but I'm gonna show you how you can tell it is wrong. Let's do it. And I want you to observe something here. So 0.289, comma 0, comma 1. Oh, I got the wrong answer. How do I know right away that I got the wrong answer?
It's negative?
Because it's negative. Very good. You are to the right of 0. How could you get a negative number if you are to the right of 0? Look at the z where I shaded. I shaded to the right of 0. It can't be negative. Then you know, guys, I mean, one way you can do when finding z-score, if you get the negative, make sure to change it to positive. You will get the answer. It's the same thing. But if I give you this as a multiple choice, guys, be assured that I'm going to put the negative part, just as a possible answer. So you got to be careful. But if you do the area to the left, definitely you're going to get a positive answer. Okay. So this is for the inverse. Okay, let's do number 9. Okay. A vet records the weights of cats treated at the clinic. The weights are normally distributed with the mean of 9 pounds and a standard deviation of 2. So the mean is 9, guys, and standard deviation is 2. Find the weight X corresponding to a Z-score. So he gives you the Z-score and he wants X. Well, here's the formula for Z, guys. We did it in chapter 2. I'm going to change this formula and make it a formula for X. So we're going to do some algebra here, cross multiplication. So Z times sigma equals X minus mean. And if I want to solve for X, guys, I'll just add the mean to both sides. So your formula for X will be Z times sigma plus the mean. Okay, let's see. He gives you a Z of 1.96. How do you find X? So Z equals 1.96, guys. X will be 1.96 times sigma, which is 2, plus 9. So that will be
12.92.
12.92. That's one. Let's do the other one. If z is negative 0.44, x would be, guys, negative 0.44 times sigma 2 plus 9, which is 8.12. If z is 0, you will be right at the mean, always. And I should get x equals 9. 0 times 2 plus 9, that's 9. So the reason why I put this exercise there to show you guys that if you have z, you have x. And if you have x, you have z, either or. Where there's a formula to change x to z, and there's a formula to change z to x. It's the same formula, but written differently. Number 10. We're still in section 5.3. Scores for California peace officers standards and training tests are normally distributed with a mean of 50 and a standard deviation, guys, of 10. An agency will only hire applicants with scores in the top 10%. So they make an announcement, only the top 10% of applicants will be hired. And you took the test and you want to figure out that you're going to be one of those top 10% who were hired. So you need to know what is the minimum score that they will accept. So what's the lowest score that you can earn and still be eligible to be hired? So to be in the top 10%. Let me do a sketch here and show you. This is the distribution of the scores. This is the mean, 50. Okay. Where do you guys think the top 10% is going to be? An area shaded in the right tail or a left tail? Right tail, exactly. I agree. And this is 10%. Okay, guys, can you help me out? How do you find X? We need to help this guy figure out whether he's gonna, let's say this guy had a score of 63. We wanna figure out, if this guy will be hired as one of the top 10%. So you need to know the minimum score that will be accepted as a top 10%. This is an inverse norm. So just do inverse norm. Remember, guys, the calculator requires the area to the left. You have the area 10% on the right. So what would be the area to the left, of X?
0.90.
Exactly. Then the mean is 50. Let's say you guys, you have a score of 63. Just I made this up. I want to see if you're going to have a chance to be hired. So let's see what X is. Second. It's very straightforward once you figure out how to work it out with the calculator. It saves a lot of time. You can do the homework in no time if you know how to use the calculator. Inverse norm, 0.9, comma, 50, comma, 10. 62.8. So it's about 62.8 score. So do you think the person who has 63 will be hired? Yes or no? The answer is yes, because it's above 62.8. And it's the lowest that will get you on the top 10% will be 62.8. And that's how you use the inverse norm. Now, I can tell you guys from my experience teaching this class, many students do not change the 10% to replace the 10% by 90. They put 10%. But I tell those students that it's very easy to figure out that your answer is wrong if you do this. So let me show you what the answer would be with 10. Enter. 0.1. Okay, guys, comma, 50, comma, 10. Watch. So here it says anyone who scores 37 or up will be higher. That doesn't make sense, guys. Why? Can't be right. Impossible to be right. How do I know that? Let's see what students say here. Very good. I have a student saying it's below the mean. Yeah, how could you be in the top 10% and you are below the mean? The mean is 50%. So that's impossible. That makes sense, yes. If your score is below the mean, you cannot be in the top 10%. You will be in the low 10%. What I did, guys, is just the bottom 10%, not the top 10%. The bottom 10% is 37 and lower. So that is, that's the answer to this question. All right, let's do a couple more questions on this from the handout I sent you. Just 1 second, let me project this. If you didn't print it out, it's still in your inbox. Once I finish this, I will provide solution to all the questions, but that will be a great practice sheet, guys, for chapter 5 and prepare you for the next test. So let me do 9 and 10, and let's do 10 first. Scores on the set form a normal distribution with mean 500 and standard deviation of 100. What's the minimum score necessary to be placed in the top 15%? Okay, guys, top 15%. If you are a top 50, this is the mean, which is what, 500? If you are a top 15%, you have to be here. And that's the 15%. What I shade is the area, which is 15%. Anyone can tell me how to find X. It's inverse norm. And 3 arguments, guys. What are they? You can type them in if you don't want to talk. 0.85. Yes, I like that. 0.85. You need the area to the left. And then 500. And then 100. If you put 15, guys, you're going to get an answer that doesn't make sense. Okay, let's do this. Let's use the other calculator and show you how to use the inverse norm in this calculator. Clear. Second, distribute. Number 3, it's the same functions, guys. Okay, area. Again, it's an area to the left. The person who programmed this should have put area to the left. 0.85. And then the mean is 500. And the standard deviation is 100. One more step, paste, and then enter. It's 603.64. So in my math lab, you might be asked to round to the nearest whole number, so just put 604. Okay, part B. Find the range of values, so minimum 2 values that define the middle 80% of the distribution. Let me show you what the middle 80% looks like, guys. This is the middle 80%. So 80% in the middle. So there are 2 values indeed. There is x1. I'm going to label them 1 and 2 because I have 2 of them. And I'm going to ask you to help me find x1 and x2. And I start, it's inverse norm. It's inverse norm. And I'll make it easier on you. Give you the last 2 arguments. 500, 100. 500, 100. The only thing are the areas. Okay. For x1, guys, this is x1 right here. This is 80%. So what remains from the curve? 20%. And the 20% is split up on both sides. This is a 10. And this is a 10. That's how the middle works. So can you guys tell me what to input for the inverse norm for x1? Okay, we got some feedback. 0.10, yes. Okay, it's going to be below the mean. This is the mean, guys, 500. So it's going to be below, definitely. And the other one, 0.90, I agree. Look, guys, how you figure it out. If this is 10%, ask yourself, what do I need to add to 10% to make it 100%? It will be 0.90. And look, guys, if this is a 10%, that means the rest is a 90%, all the way to the end. And you get the two answers. Like if I want to do the math, let me just do the math for you. Second, and distribute inverse norm 0.10 comma 500 100 paste. Okay, 371.84. That's the first one. And let's do the second one. Has to be a lot higher than this. Please use your calculator if you have it, so that you can make sure that you know how to use it when you are on your own. $628.2. Or 628 if you like. One thing, when you do your homework online, if you need help with this type of exercise, he's not going to show you how to do this using the calculator. He's going to show you how to convert, how to find a z-score and convert the z-score to an x value using table 4, etc. So that's why it's important, guys, that you be here and watch me doing this and showing you how to reduce the time by using technology to find those values. Okay. Now a question is, students always ask me, can we conclude that top 15% means the area is always on the right? Well, not necessarily. Yeah, for scores, yeah, the top 15%, it is on the right. But for a top finishers in a race, you have to be on the left, because the less time you finish, the better. So it depends on the situation. Yeah, most of the time top means going to the right, but there are situations where top means you should place yourself on the left. Number 9. The Welcher Adult Intelligence Test Scale is composed of a number of subsets. The raw scores have a mean of 35 and a standard deviation of 6. So the mean, guys, is 35 and the standard deviation of 6. Assuming these raw scores form a bell-shaped distribution, what number represents the 65th percentile? Once he gives you a percentile, guys, that means he gave you the probability and he wants the x value. So what number separates the lower 65% of the distribution? If you want to see it, it's just like this. And I have to go over 50% for 65%. So he gives you this area, guys. It's 65%, and he wants the x value. So what would be x? Inverse norm, can you guys help me and tell me what to put in there? So a percentile is an area to the left. You can write a note that it is an area to the left. You don't need to make any changes. So just use it as is. So what should I put as the first argument? 0.65, yes. Then the mean, then the standard deviation. All right, let's do it. So I'll go turn the calculator on. Inverse norm, 0.65, comma, 35 and 6. There you go, guys. 37.3. What number represents the 90th percentile? Same thing, but instead of 65, you put 90%. and change it to a decimal. I don't think it will pick it up if you just put 90 there. I never tried that, but it's not gonna understand that this is a 90%, so put 0.90. And then do the math, guys. .9, comma, 35, comma, 6. And here you go, 42.7. Okay, who can help me answer part C now? What's the probability of getting a raw score between 28 and 38? Now we're back to section 5.2, guys. We're not doing inverse norm anymore. He wants a probability. If he wants a probability, it's a normal CDF. So back to what we did yesterday. I mix, you know, the 9 both sections. 28 and 37. It should be the easiest thing for you guys when you have both a lower bound and upper bound. So this is the lower bound. This is the upper bound, this is the mean, and this is the standard deviation. Let's do that. .28, comma, 37, comma, 35, comma, 6, close, enter, and the answer is 4 decimal places, it will be 0.5089.
I have a question.
Mm-hmm.
Oh wait, never mind.
It should be 38 actually here. Let me change it. Go ahead, I'm ready to listen to you if you have any questions.
No, I figured it out, thank you.
Good. Students, if you have questions, please don't be shy to ask me. I'm here to assist you. As I told you yesterday, if I don't hear nothing, I have to assume that everything is going smoothly, whether this is true or not, but that's the assumption I have to make. 0.5698. What is the probability of getting a raw score between 41 and 44? Exactly like part C, guys. You put 41 first, the smaller number, then 44, and you do the normal CDF. 41, 44, 35, 6. You notice 35, 6, 35, 6 never changes because the mean and the standard deviation of the population are fixed. Let's do this. Okay. I'll go back and change some numbers. 41, comma, 44, and that's it. 0.09184, 0.0918. Any questions, guys? Let's do some review and do number 11. 50th grader takes a standardized achievement test. The mean is 125, standard deviation is 15, and scores a 148. What is the child percentile rank? And what percentile did he score? Meaning, what is the probability that the child scores less than 148? So what is the probability of X is less than 148? So what percent of students scored below this child? That's what we're trying to find. Okay, guys, can you tell me what the lower bound is? What the upper bound, mean, and standard deviation? This is a less than. So what do we start with if it is a less than?
Negative like a million?
Negative a million. That is correct. But let me tell you something, guys. If you put 0 here, it will work. Why? It will get the same answer, the exact same answer as negative 1 million. Does anyone know? I want you guys to think a little bit beyond the box here. I don't want you just to think it's negative 1 million and that's it, it's set. Because you know the score, can the score be below 0? It can't be, the lowest is 0. But to be safe, you can put always a negative 1 million. So, and 148, nobody can score below 0. 0 is the lowest score. Mean is 125 and standard deviation is 50. So let's see what this child's percentile rank is. I'll use this calculator. It's not an inverse norm anymore, it's a probability. Please distinguish between the two. So it's normal CDF, negative 1 million, 148, mean is 125, standard deviation is 12, paste, 97. You can say it's there's a child in the 97th percentile. What does it mean that he did better than 97% of the students? 3% of the students did better than him. That is, and I knew it was going to be a high percentile because look, the average is 125 and he scored 148. That was a very high scores. All right, I think I still have time before I do 5.4, so I'm going to do one more with you guys, just with this practice. Let's do 12, and then we'll go to section 5.4. The mean life of a battery is 50 hours, but I strongly suggest, guys, that when you get download this worksheet, just do it. Do it all, and then go back and do your chapter 5 homework. You're going to feel it as a breeze, you know, because you've already been exposed to everything. The mean life of a battery is 50 hours with a standard deviation of 6 hours. So mean is 50 and standard deviation is 6. The manufacturer advertised that they will replace all batteries that last less than 38 hours. If 50,000 batteries were produced, how many will they expect to replace? Any ideas, guys? Now we're talking behind the scenes, how they do business behind the scenes. How do they figure out how many batteries they're willing to replace, what percent of them? This is all predetermined even before they produce the product. Any ideas? They have 50,000 batteries they're gonna sell. How many of those batteries do you think will come back for replacement? We need to do, it's a two-step problem. What would be the first step? Let's do some brainstorming here. So, okay, yes. So what do you want to find, Julia? You want to find what is the probability that the battery will be replaced first. So if to figure out the number of batteries that are being replaced, guys, you need to figure out what is the chance that the battery will be replaced. So you need to figure this out. They will replace all batteries that last less than 38. So let's figure out what's the probability that X, which is a battery, less than 38 hours. Okay, that will be a normal CDF, negative 1 million. You could put 0 here because you can't have less than 0 hours battery. And then 38, then 50, then 6. Okay, let's see this. Let me do this second and distribute. Okay, this is already there, 38. And what is it? 50 and 6. Watch, guys. Okay, 0.0228. And what do I do with this percent? Now the chance that a battery will be replaced is 2.28%. We have 50,000 batteries. What do I do to figure out how many batteries are being replaced, guys? I see some ticks in the chat. Multiply it, exactly. Very good. Let me just multiply by 50 times 50,000. So about 1,138 batteries. This is how they figure out how much they can afford, you know, to replace. They figure it out in advance. And they figure it out based on this. They say, we'll replace anything that less than 38 hours. So that's how that works. All right, guys. So I'm going to stop screen sharing here. Just 1 second. And then I'm going to take you to an applet on the internet. I'd like you to watch this applet, and we're going to write, make some observations together, and then come back to section 5.4. Okay. Remember, guys, in statistics, we don't work with the entire population because it's not possible. So we collect samples. And based on the results of the samples, we draw conclusions about the population. So it's all about the samples. As you notice in sections 5.1 and 5.2, it's always been about one value has been selected. What's the probability that this value is less than this, more than that, in between? We never worked with samples, but real statistics require that we work with samples. This is the original population, that the one that you see on top. So what we're gonna do now, I'm gonna collect samples. And we're gonna ask this applet to sketch the means of each sample. For example, if I collect a sample of size 5 and I ask you to find the mean of this sample, what you do, you take the 5 quantities and you divide by 5, you get the sample mean. But we're gonna collect more than one sample. We're gonna collect thousands and thousands of samples. So when I do thousands and thousands of samples, I'm gonna need thousands and thousands of means, sample means. This is all gonna happen in the blink. Before even you blink your eyes, guys, the simulator is gonna display the results on the screen. So let me start doing some action, and I'd like you to make some observation. You have a population here, as you can see, guys, which is bell-shaped, normally distributed. You can see what the mean is. The mean is 16 and the standard deviation is 5. We're gonna collect samples of size 5. Or let me make it 10. I'm gonna ask the simulator to collect one sample and just show you how that happened with the animation. So once I click on animated, the simulator is gonna collect 10 items from the population and then add them up and divide by 10 to give me the sample mean. Watch this happening. 2, 3, 4, 5, 6, 7, 8, 9, 10. And look, it did compute the mean. Let's do another one. This is another sample mean. They're close together. Let's do another one. There you go. And so on and so forth. Now, we're gonna ask the simulators to collect 10,000 samples of size 10 and give me 10,000 means. And this is all happening for real, guys, but it's in the background of this program. Watch. And I'm gonna do another 10,000. Another 10,000. We have 40,000, if you can see on the left. We have 40,003 samples. Now, I like you guys to make observations. What you see in black is the original population. What you see in blue is the population of the sample means of X bars. I have 40,000 X bars in there. What do you notice? Just look at the two curves. Look at the values on the left and give me some observations here. What kind of observation will you make? Similarities between the two curves. How they are similar? They're both bell-shaped. Very good. They both have the same mean and median. Good. Remember, this is black is original population. Blue is the population of X bars, distribution of X bars. But notice, whether you work with the population or you work with the sample means, you're going to get the same mean, which is good. So to work with the sample means. Okay, similarities. Both curves are bell-shaped. I agree. Differences between the curves. What kind of difference do you notice? Look at the curves, guys, carefully. Can you tell what the difference is? Okay. Which one? One has a lower standard deviation. Do you guys agree with me that the data in the blue are closer together than the data in black? So
Yes.
that standard deviation is smaller. Watch, guys. Look what the standard deviation was in the original population. It was 5. Look what it is 1.59 here. But here is really the great news. The applet determined it's 1.59. I'm going to show you how you can figure out this new standard deviation without even using the applet. So grab your calculator and divide 5 by the square root of the sample size that we picked, which is 10. So if you divide 5 by square root of 10, guys, what would you get? If you can do it for me, and I'm going to do it at the same time. Okay, I got my answer. What did you guys get? 1.58, which is very close to 1.59. So observe the standard deviation is 1.59. So in order to find the standard deviation of those sample means, you take the original standard deviation divided by the square root of the sample size. Let me change the sample size now and have you look at it again. I'm going to change the sample size to 25. Okay. 25 is considered, what's considered a large sample size in statistics is 30. So 25, since this applet doesn't do 25, I'm gonna, at 30, I'm just gonna use 25 as a replacement of 30. And I'm gonna have you watch this. There is a sample, it's gonna do 25 values. Still doing 25, and then it's gonna give you the sample mean once it's done. There you go. Well, we're going to do 100,000 samples, guys. See what I'm clicking on? 100,000. Okay. What do you observe, guys? Do you observe that the mean is the same as the mean? It's still 16 and 16. Now, what I like, one curve is normally shaped, the new curve, with a smaller standard deviation for sure. Look at the new standard deviation, guys. It's 1. And look at the original standard deviation is 5. If you take 5 and divide it by square root of 25, what do you get? So you get 1 and it's already displayed. So what's the advantage of using sample means rather than using the population itself? The mean doesn't change, it's the same mean, but we will be working with more consistent population because it's narrower. The narrower, the better, the more consistent the data. And this is a great advantage of working with the sample means. It's a smaller standard deviation means a higher level of consistency and accuracy when you work with the distribution of the sample means. Now, guys, I'm going to change the population, the original population, make it not normal. Scoot. And observe what's going to happen. We're going to take a sample of size 30 or 25 here, and I'm going to do 100,000 sample. Watch. Okay, let's do another 100,000. You have 200,000 samples. Okay, The original population is not bell-shaped, but look at the population of sample means, it's bell-shaped. And we are required in most of the math we're doing here to work with bell-shaped curves. So this is bell-shaped, that's good. Look at the mean, 8.08, and look at this mean, 8.08, same mean. Standard deviation, I have 6.22, guys. I like to divide this by square root of 25 and tell me what you get because I'm using 25 here. So 6.22 divided by 5. Let's see if I have a match. I got 1.244. And look what we have here, guys, 1.25, which is pretty much the same. So even if the original population is not bell-shaped, you can still work with bell-shaped curves when we work with the X bars instead of the X values. And you have the same mean and a smaller standard deviation. Watch here now, guys. I'm gonna make it not skewed. I'm gonna make it a custom population. Just make my own. Okay, watch. The mean is 15.87. Standard deviation is 8.28. We're gonna pick samples of size 30 since no 30, 25, and see what happens. Okay, guys, watch. Mean is 15.87. The median is the same. I don't care about the median. It's mainly the mean. And look at the shape. The shape of X bars is bell-shaped again, regardless of the shape of the original population, as long as your sample size is large, 30 or more. And then, guys, take 8.28 and divide it by 5. You should get 1.65. Let me just do that. Or close to it. It's not probably going to be a match. Yeah, I got 1.656. I can add another 100,000 here. Another 100,000. I got 500,000 samples already done, guys, for me. And 16. And now if you divide 16 by square root of 25, you're gonna get 1.66. Okay, so we're gonna write our observations. Whatever we noticed here, we will write it down on the guided notebook of section 5.4. So I'm gonna stop sharing the screen and share those results with you guys. Watch the simulation demonstrated by your instructor in class carefully. That's what we did. Then write your observation below to complete the central limit theorem. Sampling distribution. What we did, guys, is called sampling distribution. Pick samples and distribute them. It's the probability distribution of the sample statistic X bar. So we're working with X bar here. It is formed when samples of size n are repeatedly taken from a population. Okay, we call mu is the original population mean, and we call the mu of X bar is the mean of the sample means. We call sigma is the original population standard deviation. Sorry, that's a mistake here. And sigma of X bar is the standard deviation of the sample means. And let's compare and contrast, the two. The mean of the sample means, guys, you notice that it is equal to the original population mean. So we write here, mean of X bar. I didn't need to prove this to you. You observed it, and that's what happened. Now the standard deviation of the sample means is equal to the population standard deviation divided by, can someone complete the blank for me here? What did I do to find it? Divided by, the sample size is n. So what do I write? Divided by what, guys? What did we do? What did I ask you to do to find the standard deviation? Square root of n, excellent. So here's what you write. This is your central limit theorem, guys. Sigma over square root of n. when the original population is normally distributed, then the distribution of the sample mean is also normally distributed. Normally means bell-shaped, guys. Regardless of the sample size can be any sample size, small or large, you will get a normal distribution of the sample means. But when the original population is not normally distributed, like Scoot, then the distribution of the sample means is normally distributed. I use the sample size 25, guys, but I told you it should be 30. So if the sample size is 30 or more. So you have a requirement. If your population is not bell-shaped, if you work with sample size and be able to apply the work using the techniques that you learn in this book, you need the sample size to be 30 or more. If it is less than 30, you cannot do it. But if your population is normal, original population is normal, sample size doesn't matter. It can be anything. So watch here at the illustration, guys. This is not a bell-shaped curve. But if we use a distribution, n is greater than 30, we get this. This is a bell-shaped curve to start with. No matter what n is, you're always gonna get that. Okay, so this is the central limit theorem. They call it the backbone of statistics. All the chapters from now on are based, just on this observation that we just made. And you will see how we put that into practice. Okay, let me do exercise 11 and show you some applications to the central limit theorem. Cellular phone bills for residents in the city have a mean of $63 and standard deviation of $11. Random sample of 100, so n is 100. Cellular phone bills are drawn from this population and the mean of each sample is determined. Find the mean and the standard error of the mean of the sample in distribution. Once he says sample in distribution, he wants X bar. Now, the mean of the sample in distribution and the standard error. The standard error, guys, means the population, the standard deviation of X bar. It's the same thing, sigma of X bar of sample means. So what he wants from you guys, he wants a mu of X bar and sigma of X bar. To find it, they're very easy. Watch, we just put the rules. Mu of X bar is mean and sigma of X bar is sigma divided by square root of n. So I'll just do it. That's a 63. And that is what? An 11 divided by square root of 100, which is 0.1. You see how smaller the standard deviation when you work with X bars? It's instead of 11, guys, 1.1 here. Instead of working with a standard deviation of 11, we're working with 1, which is 1.1, which is low. The lower, the better, guys. That's sigma of X bar. And sigma of X bar is called standard error of the mean as well. It has a different name. So if you are asked online to do the standard error of the mean, it is sigma of X bar. Another question to find the mean and the standard error of the mean. The training heart rates of all 20-year-old athletes are normally distributed with a mean of 135 beats per minute, standard deviation of 18. Random sample of size 4, so n is 4. And the mean of each sample is determined. Find the mean and the standard error of the mean. Same question, guys. So it will be 135. For this one, it's gonna be 18 divided by square root of 4. 18 divided by 2, which is 9. Now sketch the graph of the sampling distribution. Look what the graph be like this. You put 135. You call it X bar here. Okay. The mistake that some students make here, they start adding 18. You don't add 18. You want to add the new standard deviation because he wants it for X bar. So you just add 9. It would be 144, 153, and plus 9, 162. Here, subtract 9, 126, 117, and 108. And that's it. This is the distribution of X bar. Now we'll show you how to find the probabilities. 13 is very, very important question, and you're gonna see the difference between section 5.2 and section 5.4 and finding probabilities. Let's do this one. Furnace repair bills are normally distributed with the mean of 266 and a standard deviation of $15. So the mean, guys, is 266 and sigma is $15. If 36 of these repair bills are randomly selected, so now we have a sample size of 36, n is 36. Once you see a sample size, guys, he's gonna be asking you about X bar, not X. Find the probability that they have a mean cost between $266 and $268. In section 5.2, it was one bill is randomly selected. Now we have 36 of them, and he wants us to find the probability that the mean cost is between 266 and 268. So I'm gonna put 266, 268. Anyone can guess what goes in here in the center? Let's see. Oh, it's not X. He's asking for the mean, the sample mean, X bar. Yes, that is the only difference between section 5.2 and 5.4. It's about X bar, guys. Okay, look at the difference in the answers. Not much difference, guys. Watch. Lower bound is 266. Upper bound is 268. Mean is 266. And look at the difference right here. The sigma is not the original sigma, it's sigma of X bar. So it's gonna be 15 divided by square root of 36. That's a big difference here. You use a smaller standard deviation when you work with X bar right here. So I can do this in one shot, guys. Let me show you. Second, distribute. Normal CDF. So we're back to normal CDF in section 5.4. 266, comma, 268. Is that correct? Yeah. Then 266 is the mean. Then don't put 15 only. 15 divided by square root of 36, which is 6. 0.2881. So the main difference, guys, he will be asking you to find probability of X bar. You do the same work as you did before, but instead of sigma, you put sigma over square root of n. We'll do one more right here and show you how this works as well. A farmer was interested in determining how many grasshoppers were in his field. He knows that the distribution of grasshoppers may not be normally distributed in his field due to growing condition. If the population is not normally distributed, he better pick a sample size of more than 30. If he doesn't, we cannot do the problem. He says the population is not normally distributed. As he drives his tractor down each row, he counts how many grasshoppers he sees flying away. After several rows, he figures that the mean number of flights to be 57 with a standard deviation of 12. What is the probability of the farmer will count 60 or more flights on average? So once he say on average, is asking you about X bar in the next 40 rows down. So how do I do this? What is the probability that the farmer will count 60 or more on average? On average, you have to use X bar, more than 60. In the next 40 rows down. What does 40 represent, guys? Does anyone know what 40 stands for? Yes, it is N indeed. Because in each row he does a count, so he says 40 row. And N is bigger than 30, guys, so we're safe to use the central limit theorem because it is more than 40, more than 30. Okay, watch. 60 is the lower bound. Upper bound, the sky is the limit. Mean is 57. Standard deviation is 12 divided by square root of 40. Let me give you a few seconds to compute this one. So try to compute it, guys. New resume. 0.0569. Okay. So as you can see, the difference between the previous section and this section is when working with standard deviation, you use sigma divided by square root of n. I'm just gonna do a couple more exercises, guys, and wrap this up in section 5.4, so you can have a feel of how 5.4 works here. One second. There you go. It's in the handout I emailed to you. We're gonna do this exercise and then we'll wrap this up. Assume that women's height are normally distributed with the mean given by 63.6 inches and standard deviation by 2.5 inches. If one woman is randomly, no central limit theorem when you have one person. We don't use a theorem. What is the probability that her height is less than 64 inches? It's probability of X less than 64 inches. Okay, that will be, guys. Can you help me? Normalcdf. What is the lower bound? You should know by now when it is a less than. Yeah, you could put 0 or you could put negative a million. So just to be consistent, I don't want to confuse the students. I'll just put this. Because yeah, a woman's height can go below 0 anyway. So negative 10 million, and then 64, and then 63.6, and then standard deviation 2.5. And we do the math. Let's do the math here. Comma 2.5. Let me show you. And I got 0.5636. Okay, now pay attention to B, please. That's very, very important. If 36 women are randomly selected, what's the probability that their mean height is less than 64? What goes in here? He's not asking about one woman, guys. He's asking about their mean height. What's the symbol for the mean height? X bar. Very good, Ella. And once you know, guys, that there is a bar here that you know you have to change the standard deviation. Normalcdf. Look, guys, exactly the same thing. Exactly the same thing for the third argument. The only difference is here 2.5 divided by square root of 36. Let me do it. Second, distribute, normal CDF, negative a million, comma, 64, comma, 63.6, comma, and then pause here, 2.5 divided by square root of 36, which is 6. Many students forget to put the division sign in there, and they tell me we're trying to, I can't tell what's going on wrong there. It is, you have to divide there. 0.8315. All right. Next one. If one woman is randomly selected, what's the probability that her height, you see, he didn't say mean height, it's just one person, is between 60 and 65. So just do 60 less than X less than 65 and just run the normal CDF. $63.6 and then just 2.5. That's it. It's one person. You use the original population. Okay, let's do this. And I'll let you go after the next one, guys. Normal CDF, so I have 60. Comma, 65, comma, 63.6, comma, 2.5, close, enter. I got 0.6373. So the chance that you will pick a woman that her height is between 65 and 60 and 65 is 63%. Now, if you pick 16 women, what is the chance that their average height is going to be between 60 and 65? So it's X bar. Normal CDF, 60, 65, and watch, guys, the difference. Mean remains the same. The only difference is that 2.5 has to be divided by square root of 60. It's not going to be the same percent. And we'll do this. I can recall this. And then I just change the last number. 2.5 divided by square root of 16, which is 4, and close. 0.9874. On average, if you pick 16 women, the chance that their average height is going to be between 60 and 65 is very high, guys, 98%. Whereas if you pick only one person, the chance is 63.7%. Try to complete the rest of this sheet, guys. I'm going to send you the solution, worked out solution. I'll PDF it. I will send you instructions on how to turn in chapter 4. There will be a chapter 5 assignment, very similar to 4, just one question with few parts. The chapter 5 assignment will not be due until Tuesday, so I'll give you a chance to ask me questions on Tuesday, if any, before you turn it in. Next week, we will be done with chapter 6 and a little bit of 7 as well, and then we'll prepare for the test the following Monday. That is it, guys. I will stop the recording right now.